Okay, this video is going to be just kind of a general overview of the disk method about the x and the y-axis. So disk method is a way of finding volume. It's all about taking an object, whatever it is, and slicing it up into little tiny disks. And either the disk is going to look like this. I say it kind of looks like a coin or something. Or the disk is going to be sideways and going to look like this. Same thing, just turned sideways. There's some really important features on this disk, mostly the radius. So if this was our disk, we'd say here's our radius. And if this was the disk, we'd say, here's the radius. And we're going to be finding the volume. So to find the volume of a three-dimensional object, you're usually taking the area of it, so like the area of the face, so area times the thickness of the object, so however thick it is, or the width, I guess you could say. Thickness, width, kind of the same thing. In this case, a disk has the area of a circle on the front side of it here. So the area is pi r squared times whatever the width is. And these disks are going to be so small, we're going to be slicing them up and making them so skinny that the width, in reality is going to be unmeasurable because it's so skinny. It's just, we're not going to be able to give it a value. So I'm going to call it delta x. Delta x means it's a change in x that's so small that I'm going to have a really hard time measuring it. So pi r squared times delta x. Or, like in the case of this disk, it's going to be the same thing, but the width, the thickness, is going to be delta y, because it's going to be in terms of the y-axis instead of the x-axis. So the volume of this disk is going to be volume equals area pi r squared times delta y. So pretty much the same formulas, just one's in terms of x's and one's in terms of y's. When I use my radius, my r squared, I'm actually going to rewrite it as volume equals pi, and then I'm going to write a formula for r. If it's in terms of y's, it's going to be r of y squared dy. And if it's in terms of x's, like this one, it's going to be pi times r of x squared dx. And both those formulas are what we're going to be kind of working off of for our basis. So let's just do an example, kind of practice, make sure we have both methods down, x and y axis. And the first example we're going to do, example 1, we are going to take the graph f of x equals square root 9 minus x squared, and we're going to revolve it around the x-axis. So revolve around the x-axis. And we've been practicing in class all the different steps you have to go through to solve these things. Generally, you sketch the graph first. So step 1, draw a picture. So let's sketch a picture here. Now the square root of 9 minus x squared is a graph you probably should have memorized. It's a semicircle. Of course, you can do it on your calculator, and like I've plugged it in just a minute ago here, and you can see what it looks like if you want to do that. But you should kind of know that it's one of these half circles. The square root of 9, the number that's in here, is plus or minus 3. So it's one of these half circles that goes from positive 3 and negative 3 in between here. So something like this. And that's the thing we're going to be revolving. We're revolving it around the x-axis. So somewhere on the x-axis, I'm going to draw my little spinny arrow here to note that. And I'm going to label my graph. I want to do everything correctly here. So this is f of x. And we're going to spin that region around. So I'm going to shade the region. So I'll shade it in here. Hopefully you can see this yellow. And we're going to imagine cutting the region up into all these tiny, tiny little rectangles, and each rectangle is going to spin around. So I'll draw one little rectangle inside of here. Imagine there's going to be lots and lots of those. So that's step 1. Sketch the picture, shade it, draw a rectangle. Everything's looking pretty good. We go to step number 2, which is we draw the slice and the solid. We get into the 3D stuff. So the slices, if I took that one rectangle, spun it around, it's going to end up making one of these discs that look this direction. around the x-axis. So there's my slice, and my slice is going to have a radius. We'll call it capital R of x. And we're going to figure out what the radius is. That'll be our job. So we need to know what's the radius going to equal. Our solid is going to be our 3D object. So when this thing spins all the way around the x-axis, what's it going to form? So we need to draw our 3D picture. Now some people find it kind of nice to draw on the graph a little bit. So here's my half circle, and here's that little rectangle. You might find it helpful to be okay, well that rectangle is going to turn into a disc. And then imagine there's a bigger rectangle into another disc. And here's one into another disc. And here's a littler disc as it gets smaller, and a littler disc. And you might be able to kind of see okay, it's going to form kind of like a football-like shape. So I'm just going to draw okay, it's going to look something like this, like a lemon or a football, or you could put some shading on there and make it look really nice, but it doesn't have to be. You just kind of got to tell, okay, there's my 3D object, there's my solid. That's about the best my artwork gets. So we got the slice, we got the solid, we got the graph. We need a formula to represent all these discs that I was drawing have different radiuses, different lengths. So we need a formula to represent every single radius for every single disc. And I would say the radius is going to be however tall this rectangle is. R of x is the length of the rectangle, which is determined by the function f of x. However high up f of x goes, that's our radius. So really, our radius equals our function, which is the square root of 9 minus x squared. That's our radius. So let's go from here and let's set up an integral and start doing the math part of this. We've got everything drawn. Now I'm going to write our volume is going to equal an integral with pi r squared. Pi radius in terms of x squared times the thickness delta x. The bounds are going to be determined in x's, so we're going to use the x-axis, which looks pretty obvious to me, -3 to 3. So -3 to 3. And then I'm going to rewrite this integral. I'm going to pull pi out in front because it's just a number. It doesn't need to be in the integral from -3 to 3. And I'm going to change r of x into my function. I'm going to call it the square root of 9 minus x squared. That's my radius. And then I'm going to radius squared delta x. And I'm ready to go. I solved this integral and I'm going to have an answer. So let's, I guess, solve the integral real fast. I'm running out of space here, so I'm going to get another piece of paper underneath for a second. And we'll scoot this up. Okay, so nice thing is the radical squared actually cancels. So I have pi integral -3 to 3, and it's just 9 minus x squared dx. It's actually a simpler integral than it looked like at first. It's reverse power rule. I'm going to have pi times 9 becomes 9x, and minus x squared becomes minus x cubed over 3. And then the whole entire thing is bracketed from -3 to +3. And so at this point, we're going to plug everything in and get an answer. Probably easiest to plug everything in and then deal with the pi last. So I'm going to do that right here. I'm going to say, okay, keep the pi out in front, make a big parenthesis, plug in the 3, so we have 9 times 3 minus 3 cubed over 3, parenthesis, and then subtract and plug in the -3. So I'm going to have parenthesis, 9 times -3 minus -3 cubed over 3, and then close all this off. It's messy, but we can be kind of careful about this. So we got the pi in front. 9 times 3 is 27, minus 3 cubed is 27, but divided by 3 goes back to 9. So 27 minus 9, minus 9 times -3 is -27, minus -3 cubed is -27, divided by 3 is -9, so it's going to turn into plus 9. So we get equals pi times 27 minus 9 And then I'm going to factor this negative sign in. So plus 27 and then minus 9. And if I combine all this together, I have pi times 27 minus 9 plus another 27 minus another 9 is 36. So my final answer is 36 pi, which I'm going to write one more time. I'm going to clean this up and say volume equals 36 pi, and it's volume, so it's units cubed. And that is the volume of my 3D object, that football shaped thing, that solid we drew, has a 36 pi units cubed volume. And so that's how we do our about the x-axis problems. If I gave you one more example, how to go around the y-axis, this would probably be the type of problem you would see. So imagine our last example here. I give you the graph of f of x equals, how about x cubed? And I say, okay, sketch a graph of this thing. So let's sketch a graph. X cubed is the function that goes like this. I'll label it f of x. And let's say I asked you to take this graph and can you revolve it? Revolve it around the y-axis. Revolve it around the y-axis, and I say something like on, how about 1 less than or equal to x less than or equal to 3, or something like that. Okay, well, that means from 1 to 3 on the x-axis, I want to revolve it around the y. So it's kind of confusing. It means I want to spin around this axis, but I want to do it from 1 to 3. So the actual area that I'm talking about spinning is from here to here. So I'm going to shade this in, try and get a visual here. Remember, we're supposed to draw a good graph and shade everything. So here's my shading. If I'm going to spin that thing around the y-axis, I'm going to turn my rectangle the other direction. I'm going to turn it this way, which means I'm going to be forming a disk, definitely, but it's going to be in terms of the y-axis. So this is step 1. Sketch it, shade it, draw the rectangle, label everything. Now I'm going to draw my slice and my solid over here. My slice is this one rectangle spun all the way around, forms a disk that looks like this. And this disk has a radius on the inside, but it's in terms of y's. So it's r of y, represents the radius. The solid object that's going to form, let's think about what this graph is going to look like. If you want to re-sketch it over here, you definitely can. Like I said, it's sometimes kind of helpful. So here's the graph. It's x cubed. We're only spinning from here to here. So imagine like one really big disk, one kind of smaller disk, and then filling this in. You can kind of see like, oh yeah, this is what the 3D object kind of looks like. So I would say my solid is something like a little disk on top, a much longer disk there, and a connection. And there's my solid. It's about as good as I'm going to get with the solid picture there. So step 1 and step 2 done. We're ready to set up a formula for our radius and then get going on the integral. R of y is going to be determined by how long this rectangle is. R of y is how long the rectangle is, which in this case is going to be determined, yeah, by the function. It's true, f of x, but it's in terms of y's. So we have kind of an issue. You know how we have y equals x cubed is what we graphed? We want to change this to an x equals function. So what I'm going to do is I'm going to cube root both sides. Cube root both sides. So x is equal to y to the, we could say 1/3 power, which means the function is going to be my radius, but it's in terms of y to the 1/3 power when I write it. So that's what I'm going to be using for my integral setup. So let's do that. Let's set up an integral. Let's write volume equals an integral with pi r squared, but it's pi r of y squared dy. The bounds on the integral are in terms of y's, so we look at the y-axis. So I go over here to the y-axis, and I notice that it goes from this point to this point. So let's figure out where those points are. It was at 1 and 3, but on f of x. So let's see, this is at 1 cubed and 3 cubed, which is 1 and 27. So we're bounding the graph from 1 to 27, so 1 to 27 goes on my integral. And then I'll rewrite all this. So volume equals, I'll plot the pi, integral 1 to 27. I'm going to change the radius into y to the 1/3 power squared dy, radius squared. And then that's the thing I'm going to solve. So I'm pretty ready to go. It's going to be reverse power rule. I need to take the 1/3 power squared and simplify it. So volume equals pi, integral 1 to 27. This is going to be y to the 2/3 power dy. Simplify it, and then I'll reverse power rule, which means I'm going to have pi times y to the 2/3. You add 1 to that, that's going to be y to the 5/3 divided by 5/3, and then bracketed from 1 to 27. And so then I'll flip this over and clean it up. I'll say, okay, maybe I'll go over here so I actually have some space to do all this. I'll say, let's flip the fraction over and make it pi times 3/5 y to the 5/3 power, bracketed from 1 to 27. And so now plug in the bounds. I'll keep the pi out in front. I'll plug in 27. I'll say I have 3/5 times 27 to the 5/3 power minus 3/5 times 1 to the 5/3 power, all times pi. Which, might get a little messy here, but we can either plug all this into a calculator or maybe do it by hand. 27 to the 5/3 power means you're going to cube root it and then raise it to the 5th. So it's a big number. It's this is going to be pi times 3/5. It'll be 243 when you do that, minus 3/5. So times this all by 3/5, subtract the 3/5, do the math basically, and we're going to end up getting 726/5 when you clean it up. And there's a pi, so 726 pi/5. And since this represents our volume, I'll write units cubed, and I got an answer. That is the volume of the object spun around the y-axis. So disk method, that's basically the rundown. Hopefully that helped, and we'll